Hello, statisticians. Ashley here with Mostly Math, and I just want to warn you, this is a long video. This is for the people who are studying for the AP Stats exam right now and don't really know where to begin with studying. I'm going to go through the entire formula sheet, and then I have a few side notes on things that people get tripped up on, common questions, things like that. This is not something to watch in one sitting. This is like watch it, pause it, take a break, go get some coffee, do some exercising, come back. It is a commitment for sure, but totally worthwhile. This will help you improve the speed that you take the test at and hopefully your score as well. We go over a whole bunch of things that are common mistakes on the test and how to use your formula sheet, because if you don't know how to use it, you're screwed. All right, good luck. Bye. So this is the new formula sheet. This is what you're going to get when you take the test. You get it for the multiple choice and for the free response. So the nice thing is that they actually describe a lot more than they used to. So hopefully it makes it a little bit easier to follow and a little more useful. But I want to go through the formulas, and then if I happen to go off on a tangent, little mini tangent on some of this stuff, sorry, but it'll be good for you. So, number 1, descriptive statistics. Okay, so as you can see, we have the first thing is X bar, which is your mean. Hopefully, at this point, you know how to calculate a mean of a set of data. If you don't, look that up. Like, you should know how to do that. You don't need the formula. Okay. Number 2, standard deviation. All right, so we are here. Okay, we're talking about S sub X. So this is the standard deviation of a set of data that is from a sample, not from a population, right? Remember that there's a big difference between S sub X and sigma sub X. Sigma sub X is the true standard deviation for the entire population. More often than not, you're calculating a standard deviation for a sample. So, and standard deviation, again, hopefully you know already how to calculate that, and your graphing calculator can do it for you if you need to calculate it, but it is the sum of the distance from each data point to the mean. So you take data point 1, subtract the mean, you square it, and then you add data point number 2, subtract the mean, square it. You add all of those up. That's what this big old large E looking thing is. Sigma, it means sum up all of these things. So you're summing up the observation minus the mean, squaring it for all of the data points, and then dividing it by n minus 1. Okay, note that the sigma is not n minus 1. I like to think of S sub X being divided by n minus 1 to kind of get, there's actually like real math behind it, but it's about degrees of freedom. But the important piece, this important piece is that you divide by n minus 1, basically because when you're using a sample instead of a standard deviation, you want to kind of give yourself a little more wiggle room. So you're actually dividing by a smaller number to make the standard deviation larger. So S sub X, you divide by n minus 1. If it's sigma sub X, you divide by n. Okay. Important differences there. All right. Next up, so these four formulas, they're all related, okay? The first 2 are kind of related, and then these 4 are all related to linear regression, okay? Scatter plots. Y hat is equal to A plus BX, so this is an equation of a line. Y equals mx plus b, except you switch the m and the b and the a, you know, like, don't worry about it too much. Okay, we're in AP statistics. Hopefully at this point you can like deal with different variables. The slope is the one that's attached to x. Y-intercept is the one that you add separate. So this is mx plus b, but bx plus a. B is the slope. Okay. Hopefully that makes sense. My students made this mistake. They thought A and B, they were thinking it was supposed to be mx plus b, and it's not. Okay, it is the thing that's attached to x is the slope, and the thing the variable that stands all by itself is the y-intercept. Okay. Other thing that's important to note here is that your y has a hat on it. That hat means it's a prediction. Okay, it's very important that you keep the hat on there, because if you leave it off, it means you don't actually understand that y is a prediction from the x values. So your x is the independent variable. You go over the x-axis, and then you go up to find your predicted y. So keep that in mind when you are concluding in context. Oh my God, context, AP stats, everything should be in context. Okay, this is how you go from a 5 to a 3 on the exam. So always use context. Whenever you're concluding anything, you have to include the context that the problem came with. All right, if the problem's talking about paper airplanes, talk about paper airplanes. If the problem's talking about mountains, have mountains. If you're, and you should also be very clear, if you're predicting, mountain height based off of backpack weight that you're carrying, or something like that, you want to mention that we predict, if you're carrying a backpack of weight 50 pounds or something, then we predict that you're going to go on a hike, predict that we're going to go on a hike for a 14er, something like that, right? So y hat, you always want to mention that it's a predicted value and include the context, okay? So that brings us then to these other three formulas. Y bar equals A plus BX bar. Y bar and X bar are just the means of the X's and the means of the Y's. So you're plotting X versus Y. It's taking all of your X values, adding them all up, divide by how many there are, and then taking all your Y values, adding them all up, and dividing by how many there are. The reason that this is actually helpful is because sometimes they like to throw on a problem where they'll ask you to find, the y-intercept, and they'll give you some of the information. They might give you, for example, this equation. They might give you the standard deviation of y, standard deviation of x, and the correlation coefficient, and they'll give you the mean of the x's and the mean of the y's. Or you can find them because you have the data. You then would want to, they might ask you for the regression, the least squares regression line. And if you don't have the data, which you can just plug it into your calculator, you would actually use this equation to plug everything in. So in place of B, you would throw this, R times S sub y over S sub x. And then for X bar, you throw in whatever the mean is of the X's, and you throw in whatever the mean for the Y's is. And then, fun fact, now you have an equation with 3 known variables and 1 unknown variable. So you just plug them in and then solve for A. All right, so then that would allow you to produce the line of best fit. Okay, so that's typically what these are used for. That's usually what I've seen in the past when I was teaching. Okay, then that brings us to our correlation coefficient equation. So I haven't seen many questions where they ask you to calculate your correlation coefficient like this. So I wouldn't really spend a whole lot of time on that. usually they give you R, or they'll give you the data so you can plug it into your calculator and calculate R, right? Because it always you can pop it out with the linear regression on your calculator. So I'm not going to spend a whole lot of time on that one. The last one that I kind of already mentioned was this B. So this B is the slope of the least squares regression line. So that is the same as that B. Let you hang with that for a second. Those two B's are the same. So that's why I was saying that these four equations are all related because they're all plug-inable to each other. And I've only seen a few weird, like, free multiple choice questions where they give you, maybe they give you S of Y, S of X, and B, and they ask you to calculate R. And like, my students were like, what the hell is this? I don't understand. And I'm like, it's algebra. It's really easy. Don't worry about it, okay? Just like plug in the little numbers and it's all for R. Okay, you got it. So don't freak out. Just so you know, R, correlation coefficient, B, slope of the least squares regression line, and then of course S sub Y and S sub X are the standard deviation of the Y's, and then the standard deviation of the X's. So you can always calculate those, or they'll give them to you if you don't have the data. Okay. So descriptive statistics. Check. Good to go. All right, next up, probability. Whew. This is always the thing. Everybody's always like, probability. Okay, don't worry about it. You'll be fine. Probability, so these first two equations are the ones that you'll see pretty regularly. But there are some special cases, so important things to kind of note about them. So this is, remember, the upside down U is or, and the end looking thing is and. So this is the probability of A or B happening, is the probability of A happening plus the probability of B happening minus the probability of them both happening at the same time. All right. Special case is if if both A and B are mutually exclusive, so that means they don't have any outcomes in common. Think shuffling a deck of cards, pulling out and looking at the probability of pulling out an ace, shuffling a deck of cards, probability of pulling out a 2. Okay, you can't pull an ace and a 2 at the same time, so those are mutually exclusive events. On the other hand, pulling an ace, shuffling, and then pulling a red card, those are not mutually exclusive because you can have a red ace. So if I pull out a red ace, I now have counted both the ace and the red twice. So that's why you have to subtract out the probability of A and B happening at the same time. So something that my students always got confused about, they'd get confused between independent and mutually exclusive. So in this case right now, we're just talking about mutual exclusivity. So if A and B are mutually exclusive, then this is equal to 0. So you don't even have to deal with it, okay? So when you're doing these problems, sometimes they'll give you a question and they don't specify that it's mutually exclusive, but they'll ask you to find the probability, but they don't give you the probability of A and B. And then you have to think about, oh, these two things are actually mutually exclusive, and so therefore the probability of A and B is actually 0, and then it's an easy problem. Okay, so you just want to also have that in the back of your mind too whenever you're doing the probability stuff. And then you also have this other equation, which is the probability of A given B, right? The probability that A is going to happen given that B already happened. So what's the probability of me pulling an ace if I've already pulled a red card? So you already have a red card, right? And so that then changes the probability of you picking an ace in the next round. So in order to calculate that, you have the probability of A and B divided by the probability of B. Special case of this is if A and B are independent, flipping a coin. I flip it once and I get a head, and then I flip again. The next, whatever happens next, will be independent of whatever my first toss was. So if you have the two independent events, A and B, then the probability of A given B is not this. It's not the probability of A and B over the probability of B. It's just the probability of A and B. That's it. Okay. So, something else that my students got tripped up on a lot of times was, oddly enough, like algebra. So sometimes I'd see a problem where they gave the probability of A and B, and then they gave the probability of A given B, and then they'd ask you for the probability of B. My students didn't know how to solve it. Remember, this is just algebra, right? So I can multiply both sides by B and divide both sides by A given, the probability of A given B. And then you just end up with the probability of B is equal to the probability of A and B divided by the probability of A given B. So don't get tripped up on something silly like this, right? It's just algebra. It's just using another form of math in this math test, So if you feel like you don't have all the information, see if there's a special case, or see if you can manipulate the data a little bit to try to get the rest of the information. Because guaranteed, they're not going to have a problem on there that doesn't have all the information that you need on it, okay? You're just maybe missing something. So, all right, that's it for those. Moving on. All right, next up is probability distributions, looking at the mean, standard deviation. So first one is a discrete random variable x. For all of those who don't remember, discrete is like countable. I think I made a video once that was describing the difference between discrete and continuous, and a discrete random oh man, I have to sneeze. Sorry. Oh! Okay. Discrete random variable. Right, I made a video comparing discrete and continuous random variables. Discrete is countable. And in my example, we were running away from zombies. I guess I used to be super duper creative. And a discrete random variable is like how many bites you have on your arm from the zombies coming to eat you. Because you can't have half a bite, because once you're bitten, you're bitten. You're either bitten or you're not. That's it. That's all that matters. And then a continuous random variable is like how much blood loss after you got bit by the zombie. How much blood did you lose, right? Because it's like you could count, point thousandths of a liter kind of thing. So discrete random variable, you're counting, and each individual option, right? Each outcome could have a different probability. So, you're rolling a die. This is an example where, each one is the same probability, but rolling a 1, you have a 1/6 probability. Rolling a 2, you have a 1/6 probability, etc. So to find the expected value or the mean of a discrete random variable is you just take whatever the outcome is and you multiply it by its probability, and then you add up all of the options. So I'll just show you a quick little sample here. I'm going to pretend that we have a weighted die, and you have the probability of rolling a 1 is 0.1, the probability of rolling a 2 is 0.1, etc. Kind of see that. So the mean, or the expected value for this die, you would have to take 1 times 0.1 plus 2 times 0.1 plus 3 times 0.1 plus 4 times 0.3. That's what this equation is saying. So again, this typically pops up in like short answer for your response or in the multiple choice. And they just ask you, what's the mean of this, and I can't tell you how many times like my students would just like not even connect those two together. I mean, I'm making my students sound dumb. They weren't dumb. They were great. But it's like the way that the questions are worded that like really trip them up. So anyways, it's super simple. Yeah. And that's all that equation means. Remember, sigma means sum of. X sub I is the expected the outcome, and then the probability of that is the probability. So X sub I, P, and P. Okay? So you sum up, then multiplied together. All right. Now for the same distribution, we have a standard deviation. And the standard deviation is this nice, nasty, long equation, but it's really not that complicated again. So you remember your standard deviation is like how far away from the mean is every value. So you take the observation or the outcome, which would be like 1 in this case, and you subtract the mean, which we calculated in the last little section here, and then square it, and then multiply by the probability of that value. Okay, so in this case, it would be 1 minus whatever the mean was that we found, square it, times 0.1. And then we add that to 2 minus the mean, squared, times 0.1, 3 minus the mean, squared, times 0.1, et cetera, et cetera, et cetera. We add them all together. Again, we have that summation notation there. And then take the square root of it. Okay. Not horrible, but of course, when you see the equation, sometimes it can be brain overload, but it's not as hard as it looks. Okay. All right. Now we get into binomial and geometric distributions. Couple quick reminders on binomial versus geometric. In order to have a binomial situation, you need bins, and a geometric distribution, you need bits. Okay, so let me write those out for you real quick. So the difference between a binomial distribution and a geometric distribution is kind of what you're looking for. Both of them, you need to have binary data. So yes or no, black or white, 1 or 0. There's nothing, it's not continuous. You have two options, success or fail. So binary, the trials have to be independent of each other. So if you're, pulling cards out of a deck, you have to shuffle a lot of times in order for each, you have to put the card back, shuffle it again, and then repeat. You can't take it out and then take out the next card without like putting the first one back, and then it's no longer independent. And both of them need to have the probability of success has to be fixed. Your probability of success can't change from one trial to the next. And the difference between the two is that the binomial distribution or binomial setting will have a fixed number of trials. So what's the likelihood of getting 5 heads flipping a coin 10 times? Right, so you know that the number of trials you have is fixed, it's 10, and you are looking for 5 heads. The difference then the geometric words. The geometric distribution, I haven't done this in so long, my brain. The geometric distribution, the question is different. You're asking how many times do I need to flip the coin in order to get ahead? So just different question, similar types of data. The binomial distribution has parameters n and p. N is the number of trials, and p is the probability of success. And then x are all of the possible, the 0th try, first try, second try, third try, fourth try, all the way up to n. Because remember, in binomial, you have a fixed number of tries, so n is the number of trials that you've already set. And then the equation is this nx thing, means n choose x. How many ways can I take n things and choose x of them? For the geometric distribution, different situation, because you are expecting, right, you want to know the probability of getting a success on your 5th try or something like that. And all that means is that you have a fail, 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 success. And so the formula is a little bit easier. It's the probability of failing x minus 1 times fail times fail times fail times fail times fail times fail times success. And it just kind of depends on what the question asks. The mean and expected value for a binomial distribution is simply the number of trials, the fixed number of trials, times the probability of success. The mean for a geometric distribution is simply 1 divided by the probability of success. So if, for example, we're flipping a coin, a fair coin, the probability of success, let's say I want to flip ahead, the probability of success is 0.5. So 1 divided by 0.5 is 2, which would mean that the expected value of that geometric distribution is 2, right? What that means is that I expect to get a success by on my 2nd try. All right. And then last but not least, we have the standard deviation for each of those. So for the binomial distribution, it is sigma sub x is the square root of n times p times 1 minus p. Simple, just plug it in. Standard deviation of a geometric distribution is the square root of 1 minus p over p. Super simple. If you need to, take a break. This might be a long video because we're going into so much. So pause the video, go do a little dance, go check out my dance videos, do a little Zumba on the side, have a little party, and then come back, do some more math, or like go get a drink or something. I'm going to get a drink. All right, next up is looking at sampling distributions and inferential statistics. So we're now talking about the hypothesis tests. Z, T, and ChiSquared obviously is down there. That one's a little bit different. And then, when you have like a 2-sample test, you might have a couple other things happening as well. But it's always, to get your test statistic, you take your statistic minus your parameter divided by the standard error of the statistic. So the good news is that the standard error of the statistic is actually on the next page. Okay, so don't miss that. It's all here. I mean, we have it for all the different options. Note that it's broken up into like categorical data and quantitative data. So categorical data, remember, you'll be doing proportions. So you have a standard error for categorical data for one population, which is here, for two populations, which is here, and then, of course, the special case where P1 equals P2 is assumed, and then all of a sudden it makes the standard deviation a little bit easier to calculate, because you're taking out some of the complexity. If you have quantitative data, then we want to look at the means, standard error of the means. S sub x bar is S over root n. If you have two populations, then this is your standard deviation, or standard error, sorry. And then last but not least, you also have it for slope. So your test, like in this case, right, your test statistic would be lowercase b, little b, minus beta, which would be the true slope of the regression line, divided by the standard error, which is this. So you just kind of have to like look at your data and ask, okay, is it quantitative or qualitative? And are they asking for mean? Are they asking for slope? And then you just like put the little pieces of the puzzle together. And then you can just use those to get your test statistic. Right? If you have, if you're doing two samples, say you have quantitative data and you're comparing two sets of data, you're doing two samples, your statistic would be x bar 1 minus x bar 2, and then your parameter would be mu1 minus mu2. So all of these things, it changes based on what you're doing. I would highly recommend, if you haven't seen it already, watch the video that I did that's a review on hypothesis testing. That one, again, like hypothesis tests on the exam are typically like the last question, and maybe one of the earlier 5 questions, but you should know how to do a hypothesis test and how to do, like, when to do each one. So I definitely recommend watching that video. I'll post the link up there. Confidence intervals, similar, is your statistic plus or minus your critical value, which is going to be Z star, T star, whatever, times the standard error, which again, you have the standard error below. So yay, that's exciting. I love that they've like labeled everything now. Now it makes it so much easier for you. You just need to know what to plug in where. Again, your statistic could be x bar. It could be x bar minus x bar 1 minus x bar 2. It could be b. It could be p hat, or p hat 1 minus p hat 2. So again, just, you know, is it one sample? Is it two sample? Is it categorical or quantitative? And then you should be able to put the pieces together. And then, of course, chi-squared. You have your sum of the observed minus expected squared divided by the expected. And that kind of gives you your chi-squared test statistic. What is chi-squared about? Remember, we have 3 different types of chi-squared. There's the goodness of fit. Remember, chi-squared is only about categorical data. Goodness of fit, association and independence, or homogeneity. I have a video on all of the chi-squared. I have a couple videos actually on all the chi-squared stuff. So if you need a refresher on that, check out that video. There's the link. All right, so moving on, we're talking about sampling distributions and inferential statistics still. This first set here is for proportions, categorical data, means, quantitative data, and linear regression, least squares regression line, scatter plot. Okay. So something that I think is really critical to understand is what a sampling distribution is. I have another video on the difference between a sample distribution, sampling distribution, and a population distribution. And if you don't know the difference between those three things, you should definitely learn them before the test. It is one of the things that is most fundamental to understanding statistics, because you have your sample data, right? You do your experiment and you collect data, and then you can get the standard deviation, you get the mean of the data you collected, right? And hopefully that data is somewhat representative of the true population, but it's never exact, right? And so what's cool is you have these sampling distributions. So a sampling distribution is a distribution of every single possible sample of size n. So say you chose your sample to be 30. You take literally obviously this is impossible, right? This is theoretical, this is mathematical. It's not something you could actually do, but having the information actually helps us answer questions about the population, because the sampling distribution is very representative of the population itself. A sample can be all over the place. If I take 30 random people at my studio and ask them their opinions on masks, like whether or not we should dance in masks, we're going to be all over the place, especially because I'm in a super liberal town and everybody has a specific opinion, but that won't actually be representative of everyone that I'm interested in. Perhaps let's see what everybody in the United States thought about masks. My little sample of 30 people at the studio will not be representative of everyone in the US. So instead, I take the 30 people here, and then I take another random sample of 30 people in New Mexico, and then I take a random sample of 30 people in New York, and then 30 people also in New York, but a different 30 people, and you do that until you've covered every single possible group of 30 people in the US, okay? Yes, I know it's not realistic. It's crazy. You can't do that. But theoretically, you can find what the sampling distribution looks like. So that's why the sampling distribution is really, really helpful. So if you have proportions, your sampling distribution, the mean of the p-hats, which is the notation for a sampling distribution, very different than mu sub p, right? That's the true population mean. This is the sampling distribution mean. Okay. Sigma sub p hat, standard deviation, the true standard deviation of the sampling distribution. And then again, this is if you have two samples and you're comparing them, etc. Okay, same thing for the means. We have the mean of the sampling distribution is the same as the mean of the population. Don't confuse the notation. Sigma sub x bar, right, which is the standard deviation of the sampling distribution again, is sigma over root n. Here's your test statistic, your standard error, which you would use to find the test statistic. And then if you have two populations here, you have all this information, right? So, that is a lot of stuff. The last bit of it is the standard normal curve, your z-table. So you'll have that with you. And you have t distribution as well. So that'll be on there. And you have ChiSquared critical values. So you use your test statistic formula to get z or t or chi-squared or z star or t star. And then you use that, whatever your test statistic is, to then find on the appropriate chart the probability. So just keep in mind that the probability of Z within this table is the lower portion. T is going to be the upper probability for T star. So don't, get those confused. And then ChiSquared is the probability at the tail. So, and it will always be skewed right. Okay. I think that's probably more than enough for today. Holy shit, that was a lot of math. Fuck, man. Okay, bye.